I am Dr. Matthew Hartman. I am the program chair and a lecturer for the electrical engineering program here at Louisiana Tech. Dr. Long has me currently teaching you guys' ELET power related classes and all of that kind of good stuff. My office is in Nethkin Hall, room 211. For those of you who are not aware, Nethkin Hall is the building that is diagonally across from the IESB. So when you go out the main doors and you look diagonally across the street, that's Nethkin Hall. Room 211 is upstairs, way at the far end of the building towards Carson Taylor Hall and all of that kind of good stuff. My office hours are Tuesday through Friday from 2 p.m. to 4:30 p.m. I want to bring something to you guys' attention. Ada Kapanu, which is the Electrical Engineering Honor Society, for which I'm the faculty advisor, holds free tutoring for any electrical related classes from 3:30 to 4:30 p.m. on Tuesdays and Thursdays. I haven't yet found a room that will work because the damn math department took all the normal rooms I use in Nethkin for it. So as soon as I find the correct room, I'll update this and I'll send you guys an email, but you're all welcome to come and ask questions and anything like that if you need any assistance in this class. So I'm pointing this out mainly because these overlap with my office hours and I participate in these tutoring sessions as well. So I won't actually be in my office from 3:30 to 4:30 on Tuesdays and Thursdays most of the time because I'll be at this tutoring session helping people out. So just to make you guys aware of it. My email address is just my last name, HARTMANN @latech.edu. And then there's my office phone number. But realistically, you should just shoot me an email or come by during office hours or something like that because I hate talking to people on the phone. So let's see, emergency class disruption policy. Essentially, as long as we don't have another global pandemic or extreme weather event or anything like that, classes should be fairly normal. But in case one of those things happen, we will continue the class over Canvas and Zoom. Some of you may notice that I'm already on Zoom right now, so I'll be, I guess, streaming each lecture live and all of that kind of stuff on Zoom. There is a class meeting Zoom link here at the top in the introduction section in Canvas. So if you're feeling ill or just really not feeling putting on pants one particular morning and you want to participate in the class virtually, you're free to do so. Also, I record all of my lectures and everything like that, and I put them up not only on Canvas, but also my shitty YouTube channel. So if you're, if you're ill or you have to head out of town for a wedding or a job interview or something like that, you will have access to the lecture materials and all of that kind of good stuff as well. Let's see, course objectives. Essentially, we are going to learn about the title of this course, Industrial Power Distribution. So we're going to talk about single-phase systems, polyphase systems, get into applications for transformers in distribution and transmission networks and all of that kind of good stuff. This is my third time teaching the class, and I am making an effort this year, so you guys are a little bit of guinea pigs, to not hit you with nearly as much theoretical stuff and try to introduce you to more concepts that you might see out on the job. So things like how to appropriately size conductors based on equipment requirements and things like that, how to read one-line diagrams, how to fill out panel schedules, electrically related on-the-job skills that you guys might see. And then that will be supplemented with an understanding of how all these systems work together and all of that kind of good stuff. Okay. Let's see. The textbook for this class is Electrical Machines with MATLAB 2nd edition. I hope to God none of you bought this textbook because it is one of the worst things I've ever read in my entire life. That's why I put it as recommended, and even then, I don't really recommend it. For the most part, you shouldn't need a textbook or anything like that for this class because, like I said, all the lectures are being recorded. You can go back to all of them and things. That being said, if you just need to have a textbook to at least help follow along with some of the circuit analysis related concepts and things like that that we're going to be talking about, if you go to Google and you type in ULABYCAD and you go to this very first link, It's for a textbook called Circuit Analysis and Design by a few faculty members from University of Michigan, Berkeley, and the University of Utah. This book is completely free. So they are letting any student have it completely for free. If you wanted the hardback copy, they'll send it to you for only $75. I think this is a pretty good textbook for just general circuit analysis concepts and all of that kind of good stuff. So this would be what I would use personally to supplement this class because you're not stealing anybody's intellectual property. We all know you can get textbooks and all that kind of bullshit online if you look hard enough. These guys are literally giving it away, and it's a pretty damn good textbook. So this is the one that I would actually recommend for you guys if you're interested. Let's see, disability disclosure. So if you need testing or classroom accommodations based on a disability, please let me know as soon as possible. And then we'll get all that kind of good stuff set up through the Office of Disability Services. Class attendance is officially, the official policy is policy 2206 for the university, which essentially boils down to for a Tuesday, Thursday class like this, you're allowed to miss up to 2 class days without any impunity. That being said, you're all adults, you're paying to be here. If you choose to squander your opportunity to pick my brain or whatever, that's on you. So I'm not going to hold attendance against you or anything like that by any stretch of the imagination. If you feel like you'd be better served taking this class essentially from your bed instead of physically showing up, or watching the lecture videos at 2:30 in the morning because that's when you feel you can best handle electrical engineering concepts, that's all on you. As long as you show up for the tests and all that kind of stuff, you should be fine. I am going to take attendance every single class meeting because I'm required to do so. And I'm only going to consider a student present if they are physically here. But again, I'm not going to hold any absences against you or anything like that. So academic honor code stuff. This is the fairly boilerplate things that we've been dealing with the entire time we've been students here at Tech. Being a student of higher standards, you pledge to embody the principles of academic integrity. Then we have the official policy on academic misconduct, specifically behavior and cheating. How I usually boil this down to is for behavior, for lack of a better word, don't be a dick. And for cheating, don't do it. That really pisses me off, and I have no problem sending somebody up on an honor code violation and trying to get them kicked out of the university. Cheating really, really pisses me off. So do not do it. All right, regarding homeworks. So I'm going to try to assign somewhere in the ballpark of 10 total homework assignments for this class. So that'll mean you'll have roughly 1 homework assignment each week, okay? The homework assignments are going to be posted to Canvas. And I want the homework assignments to be submitted electronically. If any of you guys have ever visited my office, and I know a couple of you have, you know it is a nightmare of papers and guitars and bullshit all over the place. So paper homeworks are a bad idea because I will lose them. So everything will be submitted electronically. I want things done in engineering format. I don't know why I didn't think about this, think about it this morning, but I did not upload a homework formatting reference. So I'll do that after we get out of class here today so that you have an idea of exactly what it is that I want. The first couple of homeworks, I'll have the grader be lenient and kind of let you know how to correctly format things if you make any mistakes. But after, say, the first 2 or 3, then she'll start actually taking off points and stuff like that. I'm kind of a stickler about how I want things formatted. So I'll work with you to get you acclimated, but at a certain point, you should have figured that kind of stuff out. In-class assignments. So after some lectures, I'm going to give you guys just a brief set of problems to work here in class. And the purpose of those in-class assignments is to just let you work on problems similar to what you're going to see during your homework sets. But while I'm still here to answer any questions and things like that that you may have because you didn't catch what was going on in the lecture or something like that, okay? These in-class assignments are not graded for completeness, nor are they graded for correctness. They are essentially a participation grade, okay? So if you're here and you're trying, as opposed to being here and watching soccer on your phone or playing video games on your phone or something like that, you will get full credit for just trying to solve these problems, whether or not you get anything right. Like I said, they're kind of a precursor to the homework. It's a low stakes assignment where you're just trying to see what you didn't catch from the lecture so that you know what questions to ask so that you can be successful when you get to the homeworks, which are actually graded, okay? Also, nobody wants to hear me talk about circuits related concepts for 2 hours straight. So this is a way for us to break up me just ranting for 2 hours with you guys actually getting to do some things. So in previous quarters that I taught this class, I gave 3 exams. I'm thinking about paring that down to 2. So right now I've left it for 3. I'm just going to see how things work out with the changes I want to make to the class to add more practical content to it. So just be aware that that might get bumped down to 2, and I'll talk about it in a moment. But if I change the syllabus, I'll make sure I let you guys know and keep you up to date on any changes that were made regarding, you know, the number of exams, the wait for the exams, and things like that. For the exams, only NCEES approved or FE approved calculators are allowed. So how many of you guys have a TI-30X? So a couple of you guys are raising your hands. This is going to sound a little rude, but you need to replace that shitty peasant calculator sooner rather than later, because the overwhelming amount of math that we're going to do in this class is dealing with complex numbers and stuff like that, and those TI-30Xs are just not particularly good at that thing. So my personal preferred calculator for this class would be a TI-36X because it can store lots of variables, which is going to be quite useful dealing with all these complex numbers and bookkeeping that go along with it. It can do all of the complex math. It can also solve systems of equations for DC circuits and things like that. So it's a pretty damn good calculator. The Casio 115 is very similar to the TI-36X. The reason why I don't like it quite as much is because you have to switch modes to be able to deal with complex numbers, whereas the TI, you can just do everything from the jump. So this is the one that I prefer a little bit less than the 36X, but it is still a very good calculator. This Casio 991 that I have right here actually has been discontinued by Casio. They replaced it with an all black model that has a slightly different keyboard layout, but it has the exact same functionality. This is a good calculator. It's the only FE approved calculator that can do systems of equations that have 4 equations and 4 unknowns. So it's technically the most powerful, but for the complex number stuff that we're doing here, it's essentially the exact same powerful as the TI-36 or the Casio 115. The only thing I would warn you about with this specific calculator is that because it's discontinued, there are a lot of knockoffs that are available on websites like eBay and all that kind of stuff. Buy a used version of this calculator at your own risk. I've seen students get stuck with a knockoff, and every time they tried to input anything, it just gave them math errors and stuff like that. So it wasn't able to actually do the calculations. It was just a really good looking fake. So anyway, if you have any questions about how to use your calculator for the stuff that we're doing in this class, I'm familiar with the TI-36Xs. I'm familiar with the Casio 115s. I'm familiar with the Casio 991s. As I said earlier, the TI-30Xs are hot garbage. You should really replace that. If you need to borrow a TI-36 from me, I have a few extras in my office. So just come by and I'll let you borrow it for the whole quarter if you need it. Because I know some people might not have 20 to 25 bucks for a new calculator right now or whatever. Technically speaking, the HP 33S is also an FE approved calculator, but HP calculators confuse the shit out of me because they use some weird order of operations. I've only had like 3 students in 7 years actually use those things. So I never bothered to buy one and learn how to use it. So if you have one of those, which you probably don't, I'm not going to be much help in figuring out how to do all the math for this class. So just to recap my rant on calculators, TI-36X, great. It's the number 1, I think. Casio 991 would come in at number 2. Very, very close to the 36X, and the Casio 115 would come in just slightly behind that 991. So if you have one of these 3 calculators, you're already in great shape. Okay. Should be fairly obvious, but no cell phones are allowed to be used during your tests. And then we have our weight distribution. So this is set up for 3 exams. I'll talk my way through the logic behind it, and then we can easily see what's going to change if we go to a 2-exam paradigm. So the homeworks are worth 30% of your grade. So the bulk of your grade in this class, compared to any other assignment, is the homework problems, because I really want you guys to do the homeworks. If you do the homeworks, the exams should be rather trivial. I am of the opinion that exams should be less difficult than the homeworks, because you have more time to sit, think, contextualize, synthesize information for the homeworks. So exams should be easier than homeworks. If you've done the homeworks, the exams should be pretty straightforward. Okay. Then we have our in-class assignments. That is 10% of your grade. Then we have our 3 different exams right now. Each of them are worth 25%. And then I have a thing down here saying the weight of the exam on which you received the lowest score will be reduced to 15%. So if we added all of those things together, 30% plus 10% plus 15% for one of the tests, and then plus 25 and plus 25, that's going to come out to 105 total points. So there is effectively built into this class half a letter grade's worth of bonus already. If we go to a 2-exam modality, I will obviously adjust the weights, but it'll still be some reduction in score or reduction in weight for your lowest test, so that you can have one bad test day without it ruining your chances of passing this class and stuff like that. Okay. So I try to be pretty fair there. Every individual homework assignment and every individual in-class assignment are all weighted equally. So it doesn't matter if one set has 5 questions and another set has 2 questions, they're all worth the same amount. All that kind of good stuff. So before we move on from this little bit here, does anybody have any questions about the grading or weights or anything? All right. So I'm going to use a standard 10-point scale in this class. And notice below the grading scale, it says that there will be no curving or rounding of grades offered in this course. So I feel that because I already give half a letter grade's worth of bonus available to you guys, there's really not any reason for me to have to do any curving or rounding or all that kind of stuff, because there's things already built in to help you boost your grade. For what it's worth, I usually also have a bonus question on the exams and things like that to give you a little bit more wiggle room as well. Syllabus changes. As I mentioned earlier, I reserve the right to change my syllabus if I need to. I will make you aware of any changes that happen and all of that kind of good stuff. Then we've got some information about the emergency notification system. Sign up for it so that you're made aware of any weather events or anything like that. Cancellations due to, I don't know, in the spring, it might be tornado weather and all that kind of good stuff. Then we have the COVID-19 policy. Really, you can think of this as a sickness policy just in general. If you're sick, please don't come to class and get me sick. I've already managed to get strep and COVID this past winter quarter. I am not looking to complete the set with flu and RSV. So please, for the love of God, if you're sick, stay the hell away from me. I am tired of being ill. Obviously, as I mentioned, if you're sick, you can attend the class via Zoom, all of that kind of good stuff. Or if you don't even feel like being awake because you're so sick, you can watch the lecture videos after we have the actual class and all of that kind of good stuff. Counseling services are available for Louisiana Tech students at no charge to them. It's already handled in all the fees and all that kind of stuff you already pay. So if you need to schedule an appointment with counseling services, the link is provided here. And then even though this doesn't really apply for much in this class, I do technically have an official AI tools usage policy. It's probably similar to what you've seen in other classes, since I think this came from Dr. Long and Dr. Hall anyway. But essentially, you can use AI to help you understand course topics, to help you with solving problems and things like that. You can't use it to actually do your assignments for you, and then shouldn't really have an opportunity to use it on exams or quizzes, because A, there aren't quizzes, and B, all of the exams are going to be in person in here. And I'm sometimes not super observant, but I feel like I'd probably notice somebody pulling out a computer and using ChatGPT during a test. So if for whatever reason you do wind up using AI to help you with your homework or anything like that, just please cite that you did it. I don't have a problem with it as long as you're using it correctly and responsibly. Normally after here, I would have a tentative course schedule, but because I'm still in the mix of sorting out what practical information I want to add to the class, I'm still working out what that schedule might look like. So that's another change you'll probably see to the syllabus within the next couple of class meetings, just as I figure out exactly how many tests and stuff like that I'm going to give. Once I have that nailed down, I'll put the whole schedule out. So does anybody have any questions, comments, or concerns regarding the information on my syllabus? Okie dokie. So let's talk about some things. So I have here a basic diagram of a transmission and distribution system. This is from FERC, which is the Federal Energy Regulatory Commission. You guys don't need to copy this down or anything like that. Like I said, I'm going to make these notes as well as the video available to you. I just kind of want to talk about this so that we have some context for what this class is really about, okay? So we're going to wind up talking about essentially all of these three different parts of this overall system. That's how our electrical utility grid works. We're going to focus on some key areas, okay? So we're just going to start right now kind of reading this graph or reading this diagram from left to right. And I like how it's color coded, so it lets us know which things are associated with which different effectively divisions of an electrical utility you might wind up going to work for. So starting on the left-hand side, we have the generation side of things, right? So everything essentially, if I put a dashed black line here, everything to the left of that dashed black line is what we would consider to be generation, okay? So that includes our power plants, so generation. As well as the transformer that's used to step up our generation voltages. So we're here in Louisiana. I think Entergy itself has 89 different power plants in the state of Louisiana. Some are very, very large, some are small. Anybody have any ideas about the types of power plants that we have here in Louisiana? Or anybody had any internships with an electrical utility or anything like that yet? No idea about how the electricity that we are getting to literally have the lights on gets here. Coal, okay. So there are a few coal-fired power plants. They're not nearly as prevalent here in Louisiana as they are up towards the Virginia area because we don't have as much coal readily available down here. But there are some coal-fired power plants here in Louisiana, absolutely. There are other fossil fuel power plants in Louisiana. They're a bit more prevalent. Most of the power plants here in Louisiana are either natural gas power plants or they are hybrid power plants. So a natural gas power plant essentially burns natural gas to generate steam, which spins the turbines, generates electricity, and all of that kind of good stuff. A hybrid power plant is just a natural gas power plant that also uses effectively energy harvesting. So the heat that's generated by that burning process is also used as part of the energy generation scheme. Most of the newer power plants here in the state of Louisiana are those hybrid power plants that use both thermal generation and natural gas generation. Anything else?
Don't they have a nuclear one in like
So there are 2 nuclear power plants here in the state of Louisiana, actually. So we are one of the few states that still actually does nuclear power plants. Miss Ashton Ward, who is one of my PhD students, and she's actually going to be the person that's probably teaching this class next year because I've got to work on some ABET related stuff as a program chair. But anyway, she actually helped to design some of the systems in our newest power plant a couple of years back before she came back here to go to graduate school. Okay. Aaron Hill, who is the president of the Electrical Engineering Industrial Advisory Board, is the plant manager for one of those nuclear power plants, and he was one of the guys that helped design it and bring it up to be commissioned. So yeah, we absolutely use nuclear power plants here in Louisiana. We've got two of them. One, you're absolutely right, is the Waterford, and then I think the other one's name is something like Gulf South or something like that. I don't remember off the top of my head, but yeah, definitely got nuclear power plants here. Any other ideas about power plants in Louisiana? So we do have, I believe, one hydroelectric facility. Hydroelectric power plants are more prevalent, particularly in like the Pacific Northwest and things like that, where you've got lots of larger rivers pushing lots of water around. I don't know that there are any real large scale solar plants here in Louisiana, but I know that they're prominent, particularly in the Mojave Desert. What the hell? Sorry, I just lost the tip of my stylus. That's going to make it way harder to write things down. There we go. So you guys might have seen pictures of a big solar power plant out in the middle of Mojave Desert before. What you might not know is that Louisiana Tech students and myself actually helped design the battery energy storage system that goes along with that plant that services the Los Angeles Water and Power District. That was part of a project with Sabre Industries out of Bossier that we did a few years back. So literally tech students get to help design modern power systems. In places like Iceland and stuff like that, you also have geothermal power systems, nothing like that around here. I think they might have a couple of those plants in Canada, but particularly around here, we've got nuclear, we've got natural gas related power plants, and then we have, I think, a handful of hydroelectric plants. So anybody have any idea about the voltages that are generated at these plants? Any thoughts? Just ballpark something. So typically speaking, at a generation station, the voltages that are produced are going to be somewhere between 2 kilovolts RMS to 35 kilovolts RMS. So I'll just write that down here. So 2 to 35 kilovolts RMS. So that's not particularly high voltage. I know 35,000 volts seems like a whole hell of a lot, but that's what we would actually usually consider to be a medium voltage system. And 2000 volts is on the border of being a low voltage system here. Okay? So we generate our voltages at relatively low voltages, and then we use a transformer to step those voltages up to significantly higher line voltages. So on this particular graph, it's going in descending order from 765 kilovolts RMS down to around 138 kilovolts RMS. Typically speaking, the higher voltages are used to transmit electricity over longer distances. And we'll see the math behind why that works within the next couple of class meetings. But essentially how things work is if you step up a voltage from, let's say, somewhere in the ballpark of 10 kilovolts to 500 kilovolts, that's an increase in the voltage of about 50 times, right? 10 times 50 is 500 if my mental math is correct. Now, if you step up the voltage by a factor of 50, you actually step down the current by that same factor. So when we transmit power over long distance using these transmission lines, we're trying to do it at as high of a voltage as possible so that we're transmitting at as low of a current as possible. Anybody have any ideas why we might want to transmit power using very low currents? So that's essentially exactly right. So it has to do with the losses in the system, okay? You guys have probably heard, or at least I hope you've heard of like copper losses or I squared R losses, okay? That is essentially your conductors absorbing energy, converting electrical energy into heat as they heat up, right? So any losses that we have are related to the square of the current. So if we can get that current as small as possible, we experience the least amount of losses, which means we're wasting the least amount of money. So 100% right. It's all about heat management. Okay. So we are essentially roughly right here in our system. You guys, I don't know how many of you drive over to Jackson or anything like that on your way down towards, say, New Orleans or anything, or on your way to the, crap, that's not what I wanted to do. On your way to the beach or something like that. But particularly driving from, say, Monroe out towards Vicksburg, you might see those real big towers and all of that kind of stuff handling those distribution lines. The shapes of those towers actually will tell you what the distribution voltage is on those lines. So we'll talk about that a little bit later when we deal with three-phase power and all of that kind of good stuff. But you can literally, just by looking at the damn thing, say, oh, that's a 345 kV line, or oh, that's a 500 kV line, just by how the tower is shaped. So now we're down here where it says transmission customer. So this would really be something like a large city, something like that. So here pretty recently, there's been a lot of growth in the suburbs of Houston. So Magnolia and a couple of other places like that. So Entergy's actually introducing another 138 kV transmission station there to help service the increase in loads because of the expansion in that area. Houston itself is served by a 230 kV system because it's such a large city and all of that kind of stuff. So these large transmission customers are effectively going to be large metropolitan areas and things like that. And then as we get to cities of the size of Ruston and things like that, we're going to be on the other side of that substation step-down transformer. Okay. So everything between these two dashed lines is what would be considered the transmission side of things. And then everything to the right, we are in the distribution area, right? So this is what we deal with on a daily basis, right? So we've transmitted our electricity a very long distance, possibly hundreds of kilometers. Now we're getting close to, populated areas and things like that, or more rural areas. We're going to step it down, typically somewhere in the ballpark of, 50 to 70 kV. So the feeders that are coming into the Ruston area are 69 kV lines when they come into the Maple Street substation. And then they get actually stepped down to 13.8 kV to come into the city. Okay. Then we're dealing with primary customers. So those would be things like the large shopping centers, things like that, as well as any industrial manufacturing plants. And then we'll step things down a little bit further when we get to our secondary customers, which are single family homes, apartment complexes, and all of that kind of good stuff. Now here in the secondary customer side, it says the voltages are 120 and 240, and that's mostly true. But larger apartment complexes won't have 120 and 240 volts, and we'll talk about why it's 120 and 240 here in a little bit. They might have access to 120 and 208. That's because they are able to tap either line to line from a delta secondary of a transformer or line to neutral to get us that 120. So the ISB right here, Nethkin Hall, Bogard Hall, those are all on 120, 208 system, or actually it would be 208, 120 systems. And we'll talk a lot about three-phase power here in a little bit. May not be intuitively obvious, but if you look at the wires that are drawn in this system, there are always 3 wires going along because we use what's called a three-phase distribution system here in the United States. Anybody have any idea why we might use a three-phase distribution system? cheaper. And we'll talk about why it's cheaper and all that kind of stuff as we talk about three-phase systems. So the overwhelming majority of the design in any of these electrical systems has to do with minimizing costs. Okay. All right, so we are going to start our discussion of power concepts and all of that kind of stuff here at single phase 120 and 240, which is what we're probably all most familiar with interacting with on our daily basis as well. And then we're going to kind of expand out from there to discuss the other topics in this class, like three-phase power, transformers, and all of that kind of good stuff. So if we need to have a pretty good understanding of what single phase AC power and all of that kind of stuff, how it behaves, before we can really wrap our head around what's going on in a three-phase system and stuff like that. So this first part of the class should hopefully, crossing my fingers, be a review of some of the stuff that you guys covered in your ENGT 221 class. If it's been a minute or if you need clarification on anything, please, please, please let me know. I'm happy to try to explain things. So let's call this a review of AC power concepts. So if we start with what we are roughly familiar with, I'm going to attempt to draw a picture of a receptacle like we might see around this classroom. And I want to kind of talk about what's going on there. Okay. So here's my rather shitty representation of a single receptacle. So in a receptacle like this, this is what we would call a NEMA 15 amp rated receptacle. The one right here has this little tab out to the left on the large blade side. That means it's rated for 20 amps. We'll learn more about that and all that kind of good stuff later. But we've got essentially a plug that's rated for 15 amps, which would be the overwhelming majority of outlets that you have in your home. Okay. So I want to talk our way through a couple of simple things here. So anybody have any idea what that bottommost prong thing would be for? Ground. Absolutely right. So this is our connection to a ground bus, which is connected to literally a grounding wire in our home. That is a stake, a metallic stake that's driven into the ground that gives us a path to earth ground. Okay. So 100%, this guy is connected to our ground conductor. What about the left-hand terminal of this plug? It's the larger of the plugs where the blade from the plug itself can go in.
Yeah.
So you would think it's the hot, but that's actually the neutral. Yeah. So that is the neutral conductor. Typically that is the black wire if you were to pull the faceplate off this plug. And then the other wire is usually going to be white because the Romex that you get comes in usually white, black, and green. But I'm going to choose to draw the hot wire as red, just because you guys wouldn't be able to see a white wire on my page. So this is our hot conductor. Now, the overwhelming majority of things that we might plug into a receptacle like this actually probably wouldn't care whether or not the hot wire or the hot conductor was on the left or right. So if you ever have a plug like for these AC adapters and things like that for our computers, notice that both of the blades on the plug are literally the same size because it doesn't matter what the polarity of the voltage is or anything like that. Whenever you have a plug that has a blade that's one size larger than the other, then usually that means that the polarity actually does matter, and that's why you can only fit it in one particular way. It wasn't until I think the 1960s that they started using polarized plugs. Before then, everything just had the same size conductors. But once we started developing powerful electronics and stuff like that, we had to start actually paying attention to things. So my question for you guys right now, it's kind of an introduction to what's going on, is what would the voltage between the hot conductor and the neutral conductor be? This should be common-ish knowledge. So you may not have learned it in class, but you might have heard about it before. Yes, sir. So 120, okay? So you are both right and wrong, okay? And I'll talk a little bit about why you're right and wrong here. So when you say 120, do you mean a DC 120 volts? Or what do you mean by 120, I guess would be a good question. You don't know, you're shrugging your shoulders. That's okay. So 120 is right. That's what's called an effective value for the voltage that we use. And we'll talk about what effective values mean here in a moment. But let me ask a different question. Is the voltage that's provided by these outlets here in this classroom, in our homes and things like that, is it constant or is it changing? It's changing. How is it changing? It's a sinusoid. Absolutely right. So if we had this voltage as a function of time, V of t, this voltage would be roughly 169.7 cosine of 120 pi times time plus, I'm going to give it just a generic phase angle theta v here, where that phase angle really just is telling us when we started looking at the voltage. So if we hooked up an oscilloscope or something to one of these outlets here, what we would see is a sinusoidally varying voltage whose peak value is roughly 169.7 volts, whose negative peak value is negative 169.7 volts. So a reasonable question would be, well, where the hell did the 120 that we have heard of before actually come from? That's what's known as an effective or an RMS voltage, okay? So I'm going to hit you guys with an equation, and we're not ever going to use it for anything, so you don't even need to write it down. I just want to explain to you how gross things are going to look, okay? So just generically here, this voltage is of the form Vm cosine omega t plus theta v volts, right? So we have some magnitude, we have some angular frequency that's telling us how fast our voltage is changing as a function of time. And then we have that phase angle to let us know effectively how far away from it hitting how far away from t is equal to 0 does it hit its peak value, okay? A current in a steady state sinusoidal system like we have here in any outlet or something like that is generally going to be of the form Im cosine omega t plus theta I. So if I wanted to determine what's called the instantaneous power, that would be Do what now? Get closer. So P of T is going to be simply the product of the voltage and the current. Right? We know that P is equal to IV. We've known that hopefully for quite some time at this point. Well, if I were to multiply those two sinusoidal functions together, and I'm going to use a trig identity here, I can tell you what it is if you're interested, but I'd be willing to bet most of you won't give a shit, so I'm just going to give you the result at the end. This is going to come out to be 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I. Now, this is a big gross thing, okay, for sure. And it's really bulky and cumbersome to use. So the overwhelming majority of the time, we're not actually interested in what an instantaneous value for our power is. Like, I don't really care about, how much power is being supplied to my laptop charger at any given instant in time. I'm usually more interested in what's happening on an average basis, okay? So we can notice that this expression right here, it has two parts, okay? So we have this part right here. We'll talk about it in a little bit. And then this part right here, okay? So let's start with the part in red, okay? So we have factor 1/2. That's a constant. The magnitude of our voltage is a constant, right? So the size of our sinusoidal voltage doesn't change, just its individual value at any given point in time changes. The magnitude of our current doesn't change. Our angular frequency doesn't change. The phase angle of our voltage doesn't change. The phase angle of our current doesn't change, but there is a dependency on time here. So this part that I've underlined in red is essentially an AC power term, or we'll call it AC power term. And so this is how our power is changing as a function of time. Well, on the left-hand side, what I've underlined in blue, as I mentioned a moment ago, literally all of those different things are constant. So if theta V minus theta I is constant, then the cosine of theta V minus theta I is also a constant. So there's nothing remotely changing in time here. So we have a DC power term and then an AC power term added on top of it. Okay. So I'm going to make a little graph here that's just kind of a generic graph for an inductive load. So something as simple as a desk fan will have an instantaneous power that looks something like this. So if I plot instantaneous power, which has units of watts, as a function of time measured in seconds, my graph might look something like this. Apologize for how long this is taking me to draw. I am kind of shit at drawing sinusoids, which is problematic for an electrical engineer, but it'll be okay. So it's something like this. Now, what we have is essentially a signal that is sinusoidally oscillating above some or around some DC offset, right? So if we had just a pure sinusoidal signal, we know that it oscillates around that 0 point or the horizontal axis. But we have this DC power term that's going to raise it up by some amount. So we're going to sinusoidally oscillate around that DC term. Well, that DC term is what is commonly called the average power, because exactly half of the time our instantaneous power is above that line, and exactly half of the time our instantaneous power is below that line, right? So this represents, this dashed line right here represents our average power. So we could call this guy P average as well, if we were interested. Now, this expression for our average power is still a little cumbersome. So let me ask you guys a question. This, I hope to God, is a very simple question. In a DC circuit, what would my average power be? So it's going to be a constant for sure, but like what would my equation for average power be? So let's think about this just contextually real quick. So in a DC circuit, does anything change? No. So whatever power I have is therefore my average power if nothing ever changes, right? So how do we calculate power in a DC circuit? What's our fundamental relationship for power? P is equal to I times V, 100% correct. So instead of having P is equal to I times V, we now have this P is equal to 1/2 Vm Im cosine theta V minus theta I thing. So it's kind of related, but there's a lot more going on, right? So we're going to try to figure out how we can make that gross looking equation look a little bit more like just P is equal to I times V, okay? And we do that using what are called effective values. Okay? So an effective value So an effective value for a periodic waveform is the equivalent DC value that delivers the same amount of average power to an arbitrary load. So when we say that an outlet like we have in this room delivers 120 volts, we are talking about the effective or RMS value. So effectively, essentially that means that if we had a 120 volt DC source and we had an outlet like this, they would deliver the exact same amount of average power to any resistive load. So we use that effective value because it's a lot easier to convey that information than it is to convey 169.7 times the cosine of 120 pi t plus some phase angle volts, right? That's a whole bunch of information that really isn't needed for the overwhelming majority of things that we're actually interested in. 120 volts gets the job done, so we call it 120 volts because it delivers the same amount of average power, okay? So that's why, circling way back around, you were both right and wrong at the same time. 120 volts is correct. We just need to understand that is a representation of the AC voltage that's actually being provided by an outlet like that. So there is a mathematical equation for calculating effective values, okay? For a voltage, that relationship is V effective is equal to the square root of 1 over capital T, where capital T is the period of the periodic voltage waveform, times the integral from 0 to T of our time varying voltage signal squared, and then we're integrating with respect to time. Now, just to be real clear here, I'm not going to make you guys do this. I don't know how strong your calculus background is, and it's not particularly important for the systems that we're going to be dealing with anyway, because this actually winds up coming to a pretty simple result. I am going to make sure that I define things so that you at least know what's going on though, okay? So this capital T right here is the period of the voltage signal V of T. Anybody know what I mean by period? Exactly right. So the time it takes for our sinusoid to complete one cycle, 100% correct, right? So it takes for this 120 pi radian per second, or 60 hertz as we commonly call it here in the US, it takes about 16.667 milliseconds for each cycle. Okay, so that would be the period, 16.667 milliseconds. We take the inverse of that, it will come out to be 60 cycles per second, or 60 hertz, right? That's what electricity here in the US is transmitted at. It's a frequency of linear frequency of 60 hertz. Pretty similarly, we could find, oh, and actually let me make a note here. The units of this effective voltage are going to be in what we call volts RMS. Okay? Now, the reason why we use this different unit is so that we can easily distinguish between a regular voltage being, meaning that we're measuring it from the peak value down to the horizontal axis, versus an effective value, right? So that subscript RMS there stands for root mean squared. And that's literally just a description of the math that we're doing whenever we apply this equation, right? We are taking the square root of the arithmetic mean, which is just a fancy word for average, of the square of our voltage signal, right? So volts RMS is effectively just telling us, hey, we're dealing with an effective value, and we got that effective value by taking the root of the mean of the square of the signal, okay? Pretty similarly, we could find the effective value of a current, and it's going to wind up actually being literally the exact same expression, except instead of having V squared, we're going to have I squared. And the units for our current effective value are going to be in amps RMS. Now, how many of you guys have heard about RMS values or effective values? Did you guys cover that in your 221 class? All right, so does anybody remember how we would go from an instantaneous sinusoidal voltage to its effective value? Okay. Divide by the square root of 2 is the one that I'm more familiar with, but multiplying by 0.707 is literally the exact same thing. 100% correct. So In a sinusoidal system, V effective is simply the magnitude of our voltage, of our time varying voltage, divided by the square root of 2. And same thing for the current. The magnitude of our effective current is just going to be, our effective current value. It's just going to be the magnitude of our time varying current divided by square root of 2. So if you put that 169.7 into your calculator and you divided it by the square root of 2, tell me what you get. So damn close to 120. Yeah, absolutely right. So that's where that 169.7, that's how we make it look like 120, is we simply just divide it by the square root of 2. What's really interesting, or what's actually, I don't know if it's interesting more so than it's incredibly useful, is that for a sinusoid, like we use to do AC power in all industrialized countries, the effective value doesn't depend on the frequency of the signal, right? So it doesn't matter whether we're dealing with 60 hertz like we are here in the US, or 50 hertz like they do in most of Europe, or combination of the two, like they do in Japan, depending on which side of a river you're on because of who occupied those areas after World War II. Doesn't matter. Effective value is always just take the magnitude, divide by the square root of 2. Phase angle doesn't matter either, right? Just take the magnitude and divide by the square root of 2. So that means that the relationships that we're going to learn in this class are literally applicable anywhere that we can go work, as long as we're dealing with a sinusoidal system, which again, all industrialized countries use AC power for their grids and stuff like that. All right, so let's use these effective values real quick, okay? So let's just call this average power revisited really quickly. So up here, and I'm literally just going to be copying this down, we found out that our average power was given by the expression 1/2 Vm Im cosine theta v minus theta I. Right? Well, what we can do is we can split that factor of 1/2 up, right? So I think 1/2 is the same thing as 1 over the square root of 2 times 1 over the square root of 2. And so we could write this as Vm over the square root of 2 times Im over the square root of 2 times the cosine of theta v minus theta I, or essentially this is just our effective voltage times our effective current times the cosine of theta v minus theta I. So it's starting to look a little bit more like our DC relationship, in as much as we got rid of that pesky factor of 1/2 that just crops up because of a trig identity, essentially, right? So we have our power as effectively a representative DC voltage, V effective, times a representative DC current, I effective, but we've got this cosine theta V minus theta I thing. We can't really get rid of that because it's rather important, okay? So do any of you guys know what that cosine theta V minus theta I part represents? So did you guys talk about complex power in your 221 class? Okay. Did you use complex numbers? Let's start there. Okay. So I'm going to show you a relationship here. Let's call this section, and this is probably going to spill into our next class meeting for what it's worth, because this is kind of a big topic. We're going to call this complex power. Okay. So, since you guys are familiar with complex numbers, I'm going to rewrite that average power relationship, and then I'm going to kind of expand on it using complex numbers. Okay. So we have the relationship that our average power is equal to V effective times I effective times the cosine of theta V minus theta I. Okay, that's what we just came up with a moment ago. Do you guys remember anything about phasors? Does that sound familiar? Kind of nervous that you're saying no to that. Okay. We might have to rewind a little bit more, but it'll be okay. All right, so we'll put a pin in this thing right here. So let me do this in a different color so that we know it's a tangent, I guess. A very important tangent, but a tangent nonetheless. So earlier, I said that our sinusoidal voltages would be of the form Vm cosine omega t plus some phase angle theta v. And our currents, I of t, would be of the form Im cosine omega t plus theta I. So that if we looked at the voltage being supplied by an outlet here in this classroom, or the current that's being provided to anything that we have plugged in and it's turned on, they're going to be of that general form, right? They're going to have a constant magnitude, they're going to oscillate at a constant frequency, and they're going to have some constant phase angle depending on when we choose to look at things. And because we have that cosine omega t, we have time varying sinusoidal signals, right? So these are what are called time domain signals. And if I'm being honest, the majority of the time, we do not use time domain signals in electrical engineering because the math gets real gross real fast, right? So I gave you guys that expression for instantaneous power that had all of those different parts, and it was big and ugly and gross. It literally, that's one of the easier relationships. It just gets horrifyingly nasty. It's a lot of calculus. It's a lot of trig identities. It's a bad time for everyone involved. Okay, so we don't really use time domain signals if we can avoid it. Instead, we tend to use frequency domain signals, which are more commonly referred to as phasors. Okay. So not going through a huge explanation here because I'm hopeful that you'll recognize it once I write it down. We could represent these signals in the frequency domain by just keeping their magnitude and just keeping their phase angle and throwing everything else away, right? So our phasor voltage V would just be a complex number, Vm angle theta V, and our phasor current I would just be Im angle theta I. Is this looking a little bit more familiar now? Thank goodness. I was about to go fist fight Ron. So these are our frequency domain signals. And they are commonly called phasors. So in electrical engineering, we typically use the cosine as a reference to construct our phasors because the cosine part is the real part of an imaginary number if we were to express things in rectangular form, right? Won't go into the details, and I'm not going to be sneaky with you guys and give you sine signals and all that kind of stuff and make you transform things. We're just going to deal strictly with, excuse me, cosine signals here. So when we are doing power calculations, we actually take this a step further. And instead of dealing with explicitly frequency domain signals, we work in what's called the RMS phasor domain. So the RMS phasor domain is literally just going to be taking our frequency domain phasors and then using effective values instead of the absolute magnitude of our sinusoids, okay? So I'm going to denote an RMS phasor domain voltage as capital V with a squiggle over it, letting us know, hey, we're dealing with a sinusoidal system, okay? And pretty similarly, I'm going to deal with RMS phasor currents, I with a squiggle over it as well, so that we can tell the difference between an RMS phasor and a regular phasor, okay? So our RMS phasor is literally just our phasor voltage V divided by the square root of 2, because we know that we can take our magnitude and divide it by the square root of 2 to give us our effective or RMS value, right? So that's going to be simply Vm over the square root of 2 with an angle of theta V, or V effective with an angle of theta V. And doing something similar over here with our current, that's going to be phasor current I divided by square root of 2 is Im over the square root of 2 angle theta I will be equal to I effective angle theta I. And we call these things, or these signals, the RMS phasor domain signals. And these are the type of signals that we use exclusively for complex power calculations, all this kind of stuff. Okay, so tangent loosely over. Now we're going to talk about how we can use these things. Okay? So as it turns out, and again, stop me if you need explanation here, but I'm about to get into a little bit of complex math, or math using complex numbers, I guess would be a better way to put it. This expression for our average power, V effective times I effective times the cosine of theta V minus theta I, is actually the real part of a specific multiplication of complex numbers. Okay? So this is the real part. So that RE there just means I only want the real part of this complex thing. So if I took my RMS phasor voltage V with a squiggle over it, and I multiplied it by the complex conjugate of my RMS phasor current I would actually get my average power. V effective times I effective cosine theta V minus cosine theta I. So before we move on from here, do any of you guys remember what the complex conjugate operation actually means? So It's not that. I think you were actually talking about impedance and you got a little bit of stuff mixed up, and we'll get to that in a moment. So let's go on another brief tangent here. I'll use a different color. So let's say that I have a complex number A is equal to just A plus JB in rectangular form, or magnitude of A, angle theta A in polar form, right? I'm going to just make a note here. There's my rectangular representation, and there's my polar representation. You guys are aware that you can express a complex number either as a rectangular complex number or polar complex number, right? Okay, great. I'm going to draw that generic complex number A on a complex plane real quick. Okay. So if I had a complex plane, it would be something like this, right? So the horizontal axis represents my real numbers. The vertical axis represents my imaginary numbers, right? It's just literally two number lines 90 degrees out of phase with each other, where the horizontal axis is our real numbers and the vertical axis is our imaginary numbers. So my complex number A might look something like this, right? Where I've had to go out lowercase a units in the real direction and up B in the imaginary direction in rectangular form, or I had to go out from the origin some magnitude of A, and there's some angle theta A here, right? So these are the two different ways that I could represent a complex number. Well, A conjugate is just A minus JB, okay? So essentially, the conjugate operation just flips the sign on the imaginary part of our complex number. So if I were to draw that on my diagram, it would just look something like this, right? So here's A conjugate, where I'm still out A units in the real direction, but instead of going up by B units, now I went down by B units. What do you guys think that's going to do to our angle? Exactly right. It's just going to change the sign on the angle. 100%. Great job. So instead of having an angle of positive theta A, we're now going to have an angle of negative theta A. So the complex conjugate operation simply changes the sign on the imaginary part of a rectangular form complex number, or changes the sign on the angle of an imaginary complex number, okay? So the reason why, if I scroll back up here, I have to take the conjugate of my current is because I've got a cosine of theta V minus theta I, right? If I just did RMS phasor voltage V times RMS phasor current I and took the real part, I would wind up with V effective, I effective cosine of theta V plus theta I, and that's not what my expression should be. So we have to use that conjugate operation to put that negative sign there where we need it. So circling back around, the product of those two complex numbers, RMS phasor voltage V and RMS phasor current I conjugate, is what we're going to call the complex power. Okay. So let's put this like this. So S with a bar over it. This is our complex power. And I'm going to define this. So this is our fundamental definition. We're going to learn a few more here. Is going to be the RMS phasor current V times the RMS phasor current I conjugate. So before we expand this out, I'm telling you explicitly, I am asking you a trick question here. What are the units of our complex power going to be? So just what do you think they should be based on the fact that we're multiplying a voltage and a current together? Let's start there. Watts. So dimensionally, that is correct. But electrical engineers have decided to make up a unit for complex power so that we'll know when we're talking about complex power versus average power, because average power has units of watts, and we need to know what the difference between those two quantities is so we don't get things mixed up, okay? So the unit for complex power is what's called the volt ampere, okay? So dimensionally, it is the exact same thing as a watt. It's just a volt times an amp. But we specifically use the units of volt amperes to let people know that we're dealing with complex power as opposed to average power, okay? So I don't know how many of you guys have ever, helped your parents size a generator or anything for your house. Probably not a lot of you. But some of you might have bought, say, like an uninterruptible power supply for your computer or something like that before, okay? If you look on the box for one of those guys, it will usually have a rating that'll say something like 2100 VA, 1800 watts. That's telling you that it's rated for a complex power of 2100 volt amperes and a maximum of 1800 watts of average power can be supplied by that particular device. So this is actually something that you can see on not super regular household products, but some of the products you might have in your home, your office space, and things like that. You'll definitely see volt ampere ratings and things like that when you start looking at induction motors and things, right? They're going to have a VA rating as well as probably a watt rating and things like that, okay? So complex power is measured in volt amperes. So now I'm going to expand out this simple multiplication here. Now I'm going to be giving you guys some equations, but I genuinely don't expect you to actually have to know them, learn them, memorize them, whatever you want to call it. Because ultimately, if you can do that particular operation of just multiplying a phasor or RMS phasor voltage times the conjugate of the RMS phasor current in your calculator, and then you tell your calculator to give you the answer in rectangular form, you'll get what I'm about to give you, which is called the average power and the reactive power. And if you express your answer in polar form, you'll have what's called apparent power and your power factor angle. So your calculator can do all of this for you, so you never really need to memorize these equations, as long as you can just multiply those two numbers correctly and remember what the different parts mean, okay? So you're about to get hit with a lot of equations, which are mostly useless, but they are, I guess, technically important. So let's start with the average power, right? So we would have V effective, I effective, cosine theta V minus theta I. So that's our average power. I'll write that down in a moment, but I'm going to continue on and I'm just going to write this whole thing out in rectangular form. So the imaginary part of our complex power is going to be V effective, I effective times the sine of theta V minus theta I. So this guy right here is our average power. And as I mentioned earlier, it is measured in watts. And then this guy over here is our reactive power. and it is measured in VARs, which stands for volt amperes reactive. So now we have 3 different units for power. So if we're looking at it as a whole quantity, the complex power is a whole quantity, we're in volt amperes. If we're just interested in the real part, we're talking about average power, which is in watts. And if we're just interested in the imaginary part, then we have reactive power, which is measured in volt amperes reactive, okay? So before we talk about the differences between these different constituent parts of our complex power, I want to give you guys the symbols for these things, okay? So complex power has a symbol that's just S with a bar over it. Average power's symbol is capital P, and I usually try to put a little subscript AVG there to remind us that it is the average power, but I might not always remember to do that. So if we just see a capital P when we're dealing with complex power related things, that's our average power. Our reactive power has a symbol of Q. So essentially what we have in very simplistic terms is our complex power is just P average plus JQ. So this is what I was talking about being able to use your calculator, right? If you can multiply that voltage and the conjugate of that current together, and you get the answer in rectangular form, you get average power and reactive power. You don't need to ever use those equations with effective voltage times effective current, sine of the difference of the angles, all that kind of stuff. No need for it. If you can do V times I conjugate and your calculator gives you the answer in rectangular form, you can pull average power and reactive power just straight from that. Now let's talk about what these quantities mean, okay? So the average power is the portion of the complex power that is capable of performing work, okay? So really that's the part of the complex power that contributes to changing electrical energy into heat. So it's associated with any resistances that we have in our system, okay? Average power is literally what we pay for when we pay our utility bill every month, okay? Average power times the duration of the billing cycle is the energy that we consumed or used as a consumer of electricity. The reactive power it's the imaginary part, and it's what's associated with temporary energy storage in our system in the form of capacitances and inductances, okay? So whenever we have inductances are the dominant form of energy storage in our system, we're going to see that that reactive power term is positive. Whenever capacitances are dominant in our system, we're going to see that that reactive power is negative. So essentially, inductors are going to absorb reactive power, and capacitors are going to supply reactive power to our system. And we'll go into those relationships in a bit more detail probably next Tuesday. Okay. So you might be saying to yourself, well, since the reactive power is imaginary, why is it important? So as I mentioned a moment ago, this is how our system handles temporary energy storage. So without having enough reactive power in our system, we would actually experience frequent blackouts, brownouts, and things like that because we wouldn't be able to ride through changes in our system that happen when, say, everybody gets home from work and starts cooking dinner at the same time. Things like that are where our reactive power literally stabilizes the electricity grid and keeps the lights on, okay? So it is an integral part of our electrical utility grid. There are devices called like capacitor banks, SVCs, which I'm trying to remember exactly what that stands for, static var compensators, things like that, that are connected to large-scale industrial sites to literally help keep their lights on as they spin up their systems and all of that kind of stuff to recover from outages and things like that. Okay? So even though it's imaginary, it's incredibly important to the health of the electrical utility grid for us to have reactive power in our system. All right, any questions about this before we move over to the polar form representation? All right. So our polar form representation for complex power is going to be V effective times I effective with an angle of theta V minus theta I. Okay. Where this part right here, that's just the product of our effective values, is what's known as the apparent power. So the apparent power is literally just the magnitude of our complex power. So it just has a symbol of the absolute value of S, our complex power. And because it's the magnitude of complex power, it's also measured in volt amperes. So the easiest way to determine whether we're dealing with apparent power or complex power is whether or not there's a phase angle involved. If there's no phase angle, we're definitely talking about apparent power. If there is a phase angle, we are talking about complex power, okay? So they do use the same units because the apparent power is just a measure of how much complex power we have without worrying about the phase angle. Over here, this angle has a special name. So this is what's known as the power factor angle. We're going to talk about power factor in a lot more detail on next Tuesday's class meeting because it is a very important concept because it's effectively helping us quantify the quality in some sense of the power that we're utilizing, okay? So this power factor angle has a symbol. Sorry, that doesn't look like a theta, it looks like a Q. My apologies. Of theta S. I want to do another quick tangent here. I think this will be the last one for today, and it's mainly just a reminder for you guys. What do you remember about impedance? Have you heard that term before? Let's start there. Okay, a lot of you are shaking your heads, yes, that you've heard of impedance. That's fantastic. Anybody remember what impedance is fundamentally? So it's not the resistance, it is what's playing the role of resistance in an AC circuit, right? So when we had a DC circuit, the ratio of the voltage drop across our network divided by the current flowing into our network was the resistance of that network. Sorry, I'm not trying to throw my stylus at folks or anything, okay? Well, in an AC system, the ratio of phasor voltage to phasor current is the impedance. So it is playing the same role as resistance, but it's not just the resistance alone, okay? So just as a quick aside here, so impedance has a symbol of Z, right? And the fundamental definition for impedance is the ratio of phasor voltage to phasor current. And we can actually express this instead of regular phasors. We can put it in terms of RMS phasors as well, because that's just going to be a factor of square root of 2 in the numerator and a factor of square root of 2 in the denominator. They're going to wind up canceling each other out, right? So this could also be expressed as RMS phasor voltage V divided by RMS phasor current I. Okay? So if we use our definition for our RMS phasors, this is V effective angle theta V
divided by I effective angle theta I. And that comes out to be the ratio of the magnitudes with an angle of theta V minus theta I. And we might choose to express this as the magnitude of our impedance with a phase angle of the angle of our impedance. Now, the reason I'm bringing this to your attention is our power factor angle theta S is just theta V minus theta I, and the angle of our impedance, theta Z, is also just theta V minus theta I. So those literally represent the exact same things. So when we talk more about power factor on Tuesday, if we're only interested in a simple impedance or something like that, we actually don't have to do a ton of work to figure out complex power. We can get almost all of it just from knowing what the angle is and knowing what the magnitude of the impedance is. It's only for larger, more complex systems that we actually need to go through and bother with finding voltages, currents, and this, that, and the other. So we'll talk about all that on Tuesday. So the last thing that I want to add to this, just really quickly, and then I'll let you guys out of here a few minutes early, is the simplified version of this relationship, right? So instead of having this big ugly expression, actually this one isn't as bad, V effective times I effective angle theta V minus theta I, we can simplify this as apparent power angle, our power factor angle. So once again, if we're able to just multiply those two complex numbers together, V times I conjugate, and we get the answer in our calculator in polar form, that's giving us the apparent power and our power factor angle, and we don't actually have to memorize or learn those equations. Our calculator can do the overwhelming majority of the work for us, as long as we remember what the different parts mean, okay? We're going to kick off Tuesday's class meeting with what's called the power triangle, which is just a graphical representation that will help you remember what all of the different parts of the complex power are. All right, that's enough out of me for today. I am more than happy to answer any questions you may have. If you need any background information or help figuring out anything of this, please ask. And I swear to God, on Tuesday, we'll actually work problems with numbers and stuff so that I'm not just murdering you with relationships. Yes.